Lesson: Activation functions, key concepts and their impact. Activation functions are crucial components of neural networks, serving as the decision makers that determine whether a neuron should be activated or not. They play a pivotal role in the network's ability to learn complex patterns and make accurate predictions. At the core of their functionality is the transformation of the weighted sum of inputs into an output signal that can be used by the subsequent layer. The choice of activation function can significantly impact the performance, convergence speed, and overall effectiveness of a neural network, making it a critical aspect for any AI workflow and automation specialist to understand and master. The landscape of activation functions is diverse, with each function offering unique characteristics that can be leveraged to address specific challenges in neural network training. The most basic activation function is the step function, which outputs a binary signal based on whether the input is above a certain threshold. Although easy to implement, step functions are rarely used in modern networks due to their inability to handle nonlinear data and their lack of differentiability, which is essential for backpropagation. A more sophisticated approach is the sigmoid activation function, which maps inputs to an S-shaped curve, producing outputs between 0 and 1. The sigmoid function introduces nonlinearity to the model, allowing it to capture complex patterns in data. However, it is plagued by issues such as vanishing gradients, where the gradients of the loss function approach 0 as they propagate backward through the network. This can stall learning, particularly in deep networks, making the sigmoid less favorable for extensive architectures. Hyperbolic tangent activation function is an improvement over the sigmoid, mapping inputs to outputs between -1 and 1, effectively centering the data. This centering helps mitigate the vanishing gradient problem to an extent by ensuring that the gradients are larger, thereby facilitating faster convergence during training. Despite this advantage, tang functions are not immune to the vanishing gradient problem, especially as networks become deeper. A breakthrough in activation functions came with the introduction of the rectified linear unit, which has become the default activation function in many neural network architectures. ReLU is defined as the positive part of its input, effectively introducing nonlinearity without saturating gradients. This property enables faster training and has been shown to result in better performance in various practical applications. However, ReLU is susceptible to the dying ReLU problem, where neurons can get stuck during training and always output 0, effectively becoming inactive. To address the limitations of ReLU, several variants have been proposed, including leaky ReLU, parametric ReLU, and exponential linear unit. Leaky ReLU allows a small, non-zero gradient when the unit is inactive, which helps keep neurons alive during training. PreU extends this idea by introducing a learnable parameter to control the slope of the negative part, offering greater flexibility and potentially improving network performance. ELU further enhances ReLU by smoothing out the negative part, leading to faster convergence and improved accuracy in many scenarios. When selecting an activation function, it is essential to consider the specific requirements and constraints of the problem at hand. For instance, in a binary classification task, sigmoid activations are commonly used in the output layer to map predictions to probabilities. In contrast, softmax is preferred for multi-class classification problems, as it normalizes the output vector into a probability distribution. Practical tools and frameworks, such as TensorFlow and PyTorch, offer built-in support for a wide array of activation functions, enabling professionals to experiment with different configurations and optimize their models effectively. A case study highlighting the impact of activation functions can be seen in the field of computer vision. The advent of convolutional neural networks and the use of ReLU activations revolutionized image recognition tasks. One notable example is the breakthrough AlexNet architecture, which utilized ReLU to achieve unprecedented accuracy in the ImageNet classification challenge. This success underscored the importance of activation functions in enabling deep networks to learn hierarchical representations of data, paving the way for advancements in fields such as autonomous driving, medical imaging, and facial recognition. Despite the progress made with activation functions, ongoing research continues to explore new possibilities and improvements. The development of adaptive activation functions, which adjust their parameters during training, offers promising avenues for enhancing neural network performance. Such functions can dynamically tailor their behavior to the specific characteristics of the data and the network architecture, potentially leading to more efficient learning and better generalization to unseen data. Understanding the intricacies of activation functions and their impact on neural networks is crucial for AI workflow and automation specialists. By leveraging the right activation functions, professionals can address real-world challenges more effectively, optimize their models for better performance, and enhance their overall proficiency in building robust AI systems. As neural networks continue to evolve and find applications in diverse domains, the ability to select and implement appropriate activation functions will remain a key skill in the toolkit of any AI practitioner. In conclusion, activation functions are not merely mathematical transformations. They are fundamental components that shape the learning dynamics and capabilities of neural networks. From basic functions like the sigmoid and tanh to advanced variants like ReLU and its derivatives, each function offers distinct advantages and trade-offs. By understanding these nuances and utilizing practical tools and frameworks, professionals can make informed decisions that enhance the performance and reliability of their AI systems. As the field of AI continues to advance, staying abreast of developments in activation functions will be essential for maintaining a competitive edge and driving innovation in neural network design and application.